plot. So in this case, and here we're looking on the y-axis in terms of cumulative energy savings over the 10-year life cycle from 2012 to 2022. And the analysis shows that the initial global warming, energy, which can be translated through fuel savings to global warming potential, but the initial energy of grinding and slab replacements is very small, and that's the little bump that you can see in the year 2012, which indicates a negative value, meaning that we've invested in that construction. We then can see the payback for smooth construction, which is shown in red, for average construction, which is shown in yellow, and for poor construction, which is shown in blue. And we can see the impact of different levels of smoothness from the grinding operation on the payback for this grinding and slab replacement operation. In this case, because of the high traffic, almost any of the smoothness levels that were achieved will produce a fairly rapid payback, but the extent of that payback over the 10 years varies greatly. If we now take that same situation but apply it to a lower volume road with about 1/8 of the traffic, and analyze that, we can see in this case that because there's lower traffic, we're getting a slower payback. Because there's fewer vehicles using it, there's fewer vehicles feeling that smoothness and reducing their energy consumption. And we can see here that the payback period varies greatly in this case. It's amplified. And we can see that for the poor construction smoothness that we actually never get a payback for the investment that's made in the materials and construction. So these are just a couple examples that illustrate the kinds of analyses that can be done looking at pavement design, or in this case, potentially looking at construction smoothness specifications for the pavement design. So those examples were evaluated using mechanistic-empirical design and analysis methods, MEPDG in this case. MEPDG is a fantastic tool that allows us to look at different performance for the different decisions we make, which then impact the environmental impacts from our decisions. So ME design allows us to look at different materials. For example, the recycled content that Tom was talking about, how does that change flexural strength and shrinkage, for example, and then how do those affect performance? Looking at more locally available but potentially lower quality materials that therefore may have a lower environmental impact, or looking at some of those different types of materials that have lower global warming potential. Changes in mix design, and as I mentioned, locally available or lower quality specification materials. We can look at construction quality, such as we just saw in those examples, and we can also look at the effects of variability in construction. Then we can look at the pavement structures themselves in terms of different types of structures for different climate, traffic, and subgrade, and then the interaction with the materials and construction considerations noted above. A general approach for considering sustainability in pavement design is shown in this flow chart, which is in the reference document that was mentioned. We need to consider the inputs in terms of cost and sustainability objectives, the design inputs, and then our practices for cost assessment, sustainability assessment, and design. From that, we can develop generalized pavement type or rehabilitation approach alternatives, considering a number of alternatives with different materials, different specifications, layer combinations, etc. The next step is to complete those pavement designs using the agency's design procedures, and then figure out what the life cycle will be based on each of those pavement designs in terms of future maintenance and rehabilitation. The next step is to calculate and evaluate the performance, and from the performance, the cost and the environmental impact, and from those and from construction work zone considerations, the societal impact. And then based on that, we can modify those initial designs based on the analysis of the cost and the environmental impacts using life cycle assessment and other types of rating systems to reduce the cost and minimize the environmental and societal impacts while meeting our agency performance objectives. At that point, we have a number of optimized alternatives, and then the agency should select those based on their criteria. So that's an overview of basic approach to considering environmental sustainability in pavement design and a couple examples. And with that, we'll hand it over to Jeff Raisler to follow up.
Thank you, John.
Yes, Jeff, go ahead. And John, we appreciate the background, and Jeff is going to lead us into some discussions on pavement and rehabilitation types and design strategies. So, Jeff?
Thank you, Kurt. I'd like to talk a little bit about how we go about selecting concrete pavement types for our sustainable designs. First of all, I'd like to just reaffirm what's been stated before, that we're really not talking about eliminating certain types of pavements from the design options, but choosing ones that are more sustainable. And so as we go through this part of the presentation, we'll be looking at what are more sustainable pavements than other ones, not that ones that couldn't work. Our next what I want to talk about now was essentially how we select the candidate pavement types, and essentially, as John had previously mentioned, the types of pavements that we're going to select will have different benefits in the different phases of a pavement life cycle phase. So as we're going through the different available pavement types, concrete pavement types, we'll understand that some have better benefits than others at different life cycle phases, and it's up to the agency objectives, their sustainability objectives particularly, which ones are more beneficial. Furthermore, when we define these different pavement types, we also have to understand that we'll be making choices on the various layers in each of these pavement types, the materials we'll input, such as the recycled materials or byproduct material, co-product materials, and also the design inputs. And finally, the structural design will have to be completed on the candidate pavement types that we're going to be selecting. Ultimately, this will have to be assessed, as was noted by John's previous flow chart. So I just wanted to quickly again keep this in mind about why, as we're going through the pavement types, that really the first thing to do is understand the agency's goals and policies and determine, and those agency's policies have different objectives, one being the sustainability objectives, and that could be whether they have a rating system that has to be used, an LCA, and a life cycle cost, what the performance objectives of that roadway are in terms of a condition rating system, a cracking system, a functional objective in terms of smoothness or noise. Likewise, they may have drainage objectives for that roadway, and then they also have expected design or service lives and what they're going to do with that pavement at the end. So as we're going through the pavement types that may become candidate types to analyze, we have to keep in mind that we'll need this information from the agency or owner to actually make a good decision. I did forget a couple other ones, and that is we must make some assumptions about the construction process, which can have an impact on the pavement type and process, and also the traffic management plan. So first of all, if again the expectation is a new or reconstructed or rehabilitation, with rehabilitation, we would potentially use either a jointed plain concrete pavement or a continuously reinforced concrete pavement. And your choice within those two broad categories would be based on, again, some of the agency's objectives and their design lives, what the smoothness expectations are of the life cycle, and that may impact the use phase. How much maintenance and repair will they tolerate, and that can have an impact on the maintenance and repair phase and assessment. Likewise, future rehabilitation options that that may be planned in initially, and whether there's a policy within the agency of initial costs being a consideration versus life cycle costs. Finally, if we do a life cycle assessment, eventually this could impact what choice we would make between a jointed plane and CRC, depending on a lot of the factors I just discussed. A subset of one of these pavement types would be a composite pavement type with the two-lift concrete pavement. And one may start with, let's say, a jointed plane as an alternative, and then also move into looking at a composite pavement as a more sustainable option if there's some good reasons to do that, such as the ones I've listed here, whether there's potential use of a large amount of recycled materials in the bottom lift, whether there's only marginal aggregates available to be used primarily, and that could be used in the bottom lift, or as done in other, let's say, European countries, they may use premium concrete surfaces for noise, friction, splash spray purposes. So two-lift would be a nice impact only if there's obviously economical benefits and environmental benefits to doing so. Now, if you're moving into a longer life pavement option, and again, as John said, this in general may have the largest benefit as you look at a long horizon, but these would be used primarily, obviously, on principal arterials, and they obviously are going to require higher quality materials to be built with, more durable materials, both in terms of the concrete materials and reinforcement. And as stated by Tom, we can still use recycled materials, but this has to be more carefully assessed in the design and testing phase to make sure these materials do meet the durability requirements. The long life nature of these, and you could use a long life jointed plane. I'm just showing a long life CRCP in this case. Other features that need to be considered are drainage for the pavement, roadability of those support layers, the shoulder conditions, or the shoulder types, or the edge support conditions. If your potential pavement type may be an overlay with an overlay of a concrete pavement, one obviously always could consider an asphalt overlay, but that's also going to be determined by whether the design life of this overlay is going to be a short or longer term, whether there's reasons to not use an asphalt overlay in terms of the existing condition, elevation restrictions that may potentially be occurring, and we could also be comparing this overlay type to one of the reconstruction options I just mentioned. Also, funding resources. There may not be enough funding to choose a longer life option, such as an unbonded concrete overlay. So the second option I show there on the right is bonded and unbonded concrete overlays of an existing concrete pavement. Now, if an agency has an objective to manage their stormwater, these two types of pavements may be very good options. One being the pervious on the left, with a pervious surface and a reservoir storage underneath, and on the right is the permeable interlocking concrete pavement. And these can serve municipalities and cities very well. There are some, obviously there's some limitations to these in terms of use in lower speed roadways. This wouldn't be necessarily applicable to high speed principal arterials, at least on the main line, but they may be able to be used on potentially you could maybe use more of a pervious shoulder material. If repair and rehabilitation is an objective, and short closure windows are a must because of the traffic volume, then one type of modular pavement would be a precast concrete slab, as shown here, and they could also, and these can obviously perform very well, and these aren't necessarily considered a short-term fix at all. Now, relative to asphalt, we don't generally put thin surfaces on concrete pavements as they do asphalt pavements or different surface courses, but we do have other means to provide higher friction through tining, through grinding and grooving, or different types of turf drag approaches. and this can affect the friction, the noise, and the ability to have rapid surface runoff of the water. So these are kind of current surface options that exist on concrete pavements. So that may be something to consider if an agency really has some kind of noise objective in the life cycle. But what we may see more prevalently in the future, and I believe California has some of this in some of their has this in law, that we may have provisions for reducing urban heat island effects by choosing surface materials with higher albedos, which is essentially a measure of the surface reflectance. Also, there are photocatalytic cements out there on the market that have shown in the lab, at least, to reduce the amount of nitrous oxide on roadsides. So that could be a way of seeing concrete pavement not just as a riding surface, but also multifunctional, and to not only to reduce the temperatures in the near roadside areas, but also reduce emissions that are near roadside locations. Now, once a certain pavement type is, or certain pavement types are selected to be analyzed or designed, one still has to consider the roadway cross-section that's going to be built and how one's going to use various layers effectively. And of course, one of the big options is whether you can use support layers that utilize local recycled materials and at least local crushed materials into the pavement structure. Additionally, one has to select the construction management process such that you're most efficiently building the road to minimize the energy use in your construction phase, and also the traffic management process can have a big impact on user delays and costs associated with fuel consumption. The figure on the bottom left kind of gives you this kind of schematic of how you have to plan how you're going to go from the existing roadway cross-section to the future cross-section, selecting how we're going to specify materials or performance, and also to have strategically located areas to do the construction processing or batching of materials such that you can minimize the hauling and handling. And it's been proven by many studies that hauling and handling of these materials are a very expensive addition, energy user during the construction process. So the next slide here kind of re-emphasizes that this is transporting the materials, whether you're reconstructing or bringing materials in, or have a major environmental and social impact. And that's why writing more performance specifications, if done correctly, can help to use local materials or materials on the existing roadway into the new pavement design. And so you're seeing agencies now kind of adopt zero waste approaches to recycling and rehabbing existing pavement, so that they're using all the existing pavement in the new pavement. And one thing obviously, all this requires testing so that you're not compromising the longevity of the newly constructed pavement that you're going to select. Now, this cross section gives a kind of a good example of an existing pavement that's, for instance, could be 2 lanes going to 3 or 3 lanes going to 4, but how not only do you have to select whether I'm going to use jointed plane or CRCP, but how I'm going to use all the various materials from the existing pavement most efficiently in the proposed pavement structure, and then how I'm going to set up a construction process such that I minimize the handling of this material. And so there's many ways to think about it. Depends on whether this is an urban area or a rural area, but one has to carefully, in the design stage, think about how one can build the layers in such a way that you're going to minimize the energy used to build this new pavement structure. And setting up staging areas, helping with mobile processing are going to be ways to reduce the energy costs. Another aspect that I'll just touch briefly on is accelerated construction, that this will drive up energy consumption if construction is done more on short-term basis, weekends or nights only. And with continuous construction, you're going to reduce the cost and environmental impact by reducing mobilization, demobilization, user delay.